We already have ready Dr. Isabel Vicente Valverde from EURECAT Technology Center, affiliated to Bizeolcat project. Isabel, can you hear us?
Yes, I can hear you very clear. Okay.
Hello from Athens.
Hello from Miami, Tarragona.
A few words about Dr. Isabel Vicente Valverde before she starts presenting what has prepared for today. So she's holding a health and safety Master of Science and a PhD in chemistry by Rovira y Virgili University, Tarragona, Spain. And she gained research and development, executing and management experience worldwide by developing tailored advanced functional materials. Today, she will reach the topic synthesis, characterization, and catalytic performance of a selection of novel catalysts designed and synthesized for the Bizeolcat project. In her presentation entitled Sustainable Olefins and Aromatics by Innovative Catalysts, nanocatalysts. Isabel, you have my microphone. I'm passing it to you.
Okay, thank you very much, Veronica, for the nice introduction. Today I will talk you and I will present just a brief sample of the catalyst for the sustainable olefins and aromatics. Okay, that we prepared along the project Bizeolcat. Well, in our project, the objective was, as I said, prepare catalysts in order to decrease the greenhouse gas emissions and between other KPIs, also to use less fossil fuels, to decrease the energy consumption, and also, of course, to make this project interesting in an economic way. Okay, so it will be a greener and also more sustainable economically project. How we did that? Okay, we did that basing our approach in two novel technologies. On one side, the preparation of novel hybrid catalysts, and on the other one, on the design and the development of a reactor, a membrane reactor that could recover and valorize hydrogen. Which hydrogen? Well, it will be the hydrogen that was formed during the reactions of the hydrogenation of both propane and butane or butylene, and also the aromatization of methane.
Earlier now?
Those gases are usually used just as a flue gases for heating. Okay, but in this case, for us, we can use them as raw materials. This project, for the consecution of this project, we have a team of 13 different partners, as you can see, universities, technological centers, small companies, standardization agencies, and also big companies. Okay, such our two Professor. And well, what we did, as I said, the propylene, butadiene, and also the aromatics are very important in our daily life because they are building blocks for almost everything. And from that, what we can obtain are plastics like polypropylene or ABS, like for toys, for packaging, also the polystyrene, and also fibers, or like for polyurethane for recoveries and other purposes, and even also for tires or tubes, but you can see that those are products that are in our really daily life. Okay. However, the point is that these products are usually obtained by the naphtha cracking, and this is a process that has related very high emissions of CO2 and also very high use of energy. For this, the alternatives are these three processes that are the propane or butane dehydrogenation and also the propane aromatization. Okay. These processes are already on the industry. And here I show one of the most relevant of them. It's important to remark that all these processes are equilibrium. And in the case of the propane dehydrogenation, I show you two different processes with catalyst based on both chromium, with all the safety issues that it has, or platinum tin. In these cases, temperatures of the process are high, so it's a very high energy consumption. Again, for the butane dehydrogenation, we have also a chromium catalyst. And in the case of the cycler, it's a gallium catalyst, but in the case, again, the temperature reaction, since though all of them are highly endothermic reactions, we need very high temperatures. Okay, so to overcome this, we prepared novel catalysts. First of all, I will have to say that I will show you just a very brief sample of the catalyst we have prepared. Okay, this is because we have many and I try to make it simple for this presentation. So the first one is the one developed in EURECAT, which is the one-pot organometallic approach. And as you can see in the slide, what we did was in the reactor to mix the metallic precursors, that would be platinum and tin, to prepare nanoparticles of platinum and tin onto the support. That could be, in this case, alumina or zeolites. And also we use some ligands that will be act as stabilizing agents. So we place all together. And in this case, what the ligands do is both the ligand and the support will control the decomposition of these metallic precursors. So we can have a very controlled nanoparticle with a very controlled properties. We can monitor this reaction by GC by looking at the butene that comes from the decomposition of tetrabutyltin. Here I show you an example of some of the catalysts that were prepared, yes, as I say, with platinum tin, using triple phosphate or carbene as catalyst. The difference, or in the case of the triple phosphine, are those all on beyond, which are the supported onto aluminas or zeolites. Okay, in this case, as you can see, the size of the particles obtained was very similar, and the distribution of the particle size was narrow. More to say from EDX analysis is that in this case we could observe that the ligand is only interacting with the metal nanoparticle, while the tin is homogeneously placed onto the support and also on the ligand. Okay. When looking at the catalytic performance, in this case for the propane dehydrogenation, what we could observe is that we have conversions similar to those on the benchmark process. Moreover, is that the conversion can be related to the tin platinum content on the catalyst, and as we can see, for the highest tin contents, we can observe highest conversions, while the selectivity, which is very high, and in the case of the aluminas, which is almost 100%. And this reaction, you can see, was for 3,000 minutes. the selectivity is very stable for the whole reaction time. Other catalysts that were prepared, and again, I say this is just a very brief sample because many different catalysts were prepared by these two methodologies. While the single-site catalyst in this case, okay, prepared by surface organometallic chemistry. Those catalysts were developed by the laboratory, the CP2M, which is in the CNRS. And in this case, what they used was, in this case, a vanadium, but could be other complex. So by reaction with the support, and after we can obtain a monopodal species, and afterwards by thermal treatment, we can obtain several different species, bi or tripodal. Okay, depending on the thermal treatment. In this case, I will show you some examples with the vanadium catalyst, single-site catalyst supported onto silicate. Okay, this reaction of the preparation of the bi-tripodal catalyst, single-site catalyst, was monitored by drips, was characterized by drips and NMR. In the case of the drip, if we see the first red line in which we have the monopodal species, as we can observe increase in the temperature, what we observe is one band which is related to the silanols, and another band which is related to the vanadium hydroxyl signal. Okay, so what we can observe here is that the butoxyl or the alkyl part goes off, and the vanadium gets interaction or gets grabbed into the support. We can compare this also by the proton NMR, in which the signal related to alkyl disappears and appears one related to the silanol groups, and by vanadium that we can observe. In the case we begin here is the beginning is the one up above, and we can observe is the signal appears or it displaces that is attributed to the single vanadium species. Okay, in this case, what we could use for this catalyst was, for example, for the reaction of propene dehydrogenation. Okay, in this case, what I have here is the results of the catalyst at two different temperatures of the thermal treatment for the preparation of the single-site catalyst. What you can observe was that when increasing the thermal treatment from 200, which is the red line in the middle graph, to 700 degrees, from red line, this is, sorry, 700 degrees to 200, when decreasing the temperature, okay, we have a higher conversion, and also when decreasing the temperature, we have a slow high selectivity also. It is remarkable that the conversion can be comparable again to those in the benchmark process, and also selectivity is quite high. This catalyst it can be used, as we've seen, for the propane dehydrogenation, but can be used for butene dehydrogenation. Yes, well, as you can see here, with the best catalyst for propene dehydrogenation of this series, okay, was also tested for butylene dehydrogenation, and we can observe is that after 400 degrees, the conversion is stabilized at around 15%, okay, and also the selectivity remains high to the butadiene and stable around all the tests time. As we can see, we can use those single-site catalysts for the hydrogenation reactions, but also, okay, for aromatization. In this case, I won't give many details. I will just, that is a metallic single-site catalyst supported onto zeolites. Here we have two different stupors, okay? And what we can observe here in this reaction is a very high conversion, as you can see, above around 70%, and that gets stable even after 3,000 or 100 minutes, after a very long time of reaction. And also the selectivity remains very stable along the whole process. Okay. So, well, just concluding, we can say that new catalysts were designed for these three different processes that were the PDH, the VDH, and the aromatization, and obtaining high conversion, selectivity, and stability results. I will remark also that here I just placed the lab scale results because our companies from Tupras this afternoon will explain you about the scaling up process. So this is just the lab scale results. And in the case of the one-pot organometallic approach, as you could say, that when in the synthesis, the decomposition of the tin was affected by the support. It can be also the ligand, and afterwards, when looking at the catalytic performance, we could observe that the tin is directly related to the conversion of propane, but the selectivity is affected by the support. And finally, for the case of the surface organometallic catalyst, we could observe that the thermal treatment led to a triple vanadium, and the temperature of this treatment, for the triple vanadium catalyst onto silica at lower temperatures, at 200 degrees, seem to get to better catalytic performance that we obtaining on silica. And this should be, yes, related to some structure or some relationship between the silica and the vanadium. And well, finally, last, I would like to thank CP2M laboratory from CNRS, also EURECAT, our group, and here this a small sample of our Bizeolcat colleagues, because it was a very nice adventure for 4 years that finished in December last year, and also to you for your attention. Just to see, here we have my contact, and also contact from Professor Mostafa Tofik from CP2M lab in Lyon. Okay, thank you.
Thank you very much for sharing your work. I would please ask you to stay a little bit more for some questions. There is one already from our online audience.
Mm-hmm.
And the question is, in your test on butene dehydrogenation, is there isomerization to isobutene and formation of aromatics?
What we have most was butadiene, and afterwards on the composition products that could be ethane or ethylene, but as you can observe here, there are no aromatization products. As I can see also, I have to see here that maybe these are not the best catalytic performance results we had, and this is just a sample, okay? So just to summarize, so this is one catalyst that could perform for different reaction. I don't know.
Yes, thank you for answering. These were all the questions we had online. Any questions from the room? We do have one from Dr. Cazaros.
Mm-hmm.
Thank you, Isabel, for the nice presentation. and the results you showed us. I want to ask if there is any effect of the pore topology or ordering of the silica support on vanadium catalysts regarding the efficiency and selectivity of the catalyst.
That's a very good question. Okay, I think for that particular case, we didn't study that because, as I said, this was like some example for the catalyst, for the whole catalyst. So those were not the most studied.
Okay, so it was just a silica, amorphous silica sample.
Yes, it was amorphous silica sample, and we didn't study that in deeply.
Okay, and regarding the catalyst with platinum and tin, is there any alternative for this reaction without using critical raw materials? In general, it's not related to your work or to the work.
Yes. Of course, yes. We studied also other methods. Okay, but the best results were obtaining with this catalyst. we will learn that we can say this, that even those are used with raw materials. Okay, which is not the best, as you can say. They are very stable, so we can use them for many time. They are low platinum content. So yes, we had another ones, but in the case of the platinum tin, those were the best results. As you can see in the case of the vanadium for propan dehydrogenation, the selectivity for the catalyst was not as high as in the case of the platinum tin one, and that's why we went for the platinum tin ones. But yes.
Okay, thank you very much. Thank you.
Thank you again. Do we have any other questions from the room? Hi, then I will thank you again, Isabel, Vicente, Valverde. It was a pleasure having you today.